Okay, welcome back to the last session for the morning of today. We are pleased to have Frank Piessens to talk us about introduction to software security, and after that we have lunch. Thank you.
Welcome to this introductory lecture on software security. So maybe 1 minute about myself. So my name is Frank Piessens. I'm a professor here at the Department of Computer Science in the University of Leuven. And my research area is software and system security. So today's lecture will be introductory. So I hope it will be easy to follow even for people without a deep technical background. But this is also my area, so if you have more deep technical questions, you're welcome to ask them at the end or to grab me after the talk and ask questions. Okay, so the lecture today is introductory. How will I attack this introduction to software security? Well, here is a plan for the talk. So what I'll do is I'll first spend a bit of time explaining the general process of security engineering and all the concepts that are important there. And I hope this will be useful not only for this particular lecture, but maybe also for some of the later lectures in this course. So understanding the key concepts of security, things like asset, risk, threat, control, and so forth, is useful beyond just software security. So I'll spend a fair amount of time on that to make sure that we're on the same ground, try to give plenty of examples. Don't hesitate to interrupt me and ask questions if anything is unclear. And then at the end, I can say, well, what is software security? Well, one possible definition is security engineering for software-based systems. Right? And that's essentially what we'll explore in the second part of the talk. So that's one possible definition of the field of software security is security engineering for software-based systems. And we'll illustrate that by looking at some of the key controls that matter for software security, things like isolation or sandboxing, authentication, authorization, and so forth. However, there's a second possible definition of software security that's more about what the security issues you run into when you are developing software yourself, right? And these are software implementation vulnerabilities. And software security is sometimes defined more narrowly as studying these implementation vulnerabilities, how they can be exploited and how you can defend against them. And that will be the third part of the talk. I'll take this more narrow view on software security, explain what implementation vulnerabilities are, why they are important, give you a couple of examples, again, all at the introductory level. But I hope to bring across why this is indeed a very important facet of software security, to the extent that sometimes this is how people define the entire field. Okay, and then I'll end with a brief conclusion and maybe some time for questions. Okay, that's the plan. So as I said, interrupt me at any time if you want. I know in a big group that's not always easy, but I'm happy to be interrupted. So if you have questions, just shout. Okay, so the general security engineering problem. So if you're building or analyzing a system, to have a security problem there means that at least 3 key things have to be present, right? So the first thing is there must be something of value in the system. That's what we call the asset here. If there's nothing of value in the system that you're building or analyzing, there's no security issues, right? Of course, value is a relative thing. So if there is something as value, that means it's valuable to somebody. We call that here on the slide the owner or the defender that values or protects these assets. So that's a second concept you need to see in the system somewhere. What stakeholders value these assets, right? And we'll see a common thing in security is that different stakeholders may have different protection requirements for the same asset. And as a security engineer, it's up to you to resolve these tensions and trade-offs, right? And finally, a third ingredient that's absolutely essential to have a security problem is you need an adversary. If there is nobody after your assets, if nobody is trying to abuse, steal, or damage your assets, you don't have a security problem. You may have a reliability or a safety problem or whatever, but in security, a core assumption is that there is an intelligent, strategic adversary explicitly trying to get to your assets. So when you are building or analyzing your system, you have to take that into account. And it's harder to defend against a strategic, intelligent adversary than it is to defend, for instance, against natural disasters like earthquake or fire, because these will not analyze your system and find the holes in it. Okay, so these are three core concepts, and let me illustrate them on a high-level system that everybody knows, a messaging system, something like WhatsApp or Signal or email even. What would be assets in such a system? Well, plenty of things could have value to some stakeholders. So obvious things are things like the content of messages. You may want to protect the content of messages that you send in the sense that not everybody should be able to see them. Metadata, you may not want others to know who you are communicating with. But also maybe the service itself, maybe your business depends on the availability of WhatsApp. Maybe orders are processed through WhatsApp, so the availability of the service may be of value to some stakeholders. And then infrastructure, network infrastructure, the hardware on which all these things run will be valuable to some stakeholders. Right? And this is actually a very typical list of assets in an IT-oriented system. You have three types: information, services, and infrastructure or hardware. Right? So these are typically the core things that have value in a computer-based system. Who are the stakeholders caring about these assets? Again, there can be many, and I just list a couple of obvious ones. So obviously, for instance, the platform users, the people sending the messages are the ones that will care about message content most, maybe. The platform provider, of course, will be a stakeholder, and this is a good example of two stakeholders with potentially conflicting requirements. So you, as a platform user, may want to protect message content in the sense that nobody can see it except you and your recipients. That's a reasonable protection requirement, privacy inspired maybe. But the platform provider may have another protection requirement saying I want to be able to look into all messages to make sure that no illegal activity is happening on the platform. For instance, looking for child porn being distributed over the platform or whatever. You all know this tension. This is a good example of a tension between two stakeholders about the same asset. One wants it to be private and the other wants it to be visible, right? And these kinds of tensions occur. They're unavoidable in a security setting, and they will have to be resolved when you are looking at the system as a security engineer. Okay, and finally, who are the adversaries in the example of a messaging system? Well, they're, again, the obvious ones. So for a messaging system, typically your immediate social circle is the first adversaries you should think of. The people interested in your messages are your family, your colleagues, your partner, and so forth. But at a very different scale, it might be intelligence services looking for terrorists. It might be criminals trying to find ways to defraud people using this messaging platform, and so forth. So again, you can come up with a very open-ended list of adversaries. So these are three core concepts. Of course, they're relevant in any security setting, not just computer-based security. What we are interested in computer security or in cybersecurity is how does the use of a computer system influence the risk that the assets that we identified run? Yeah. So for example, if I have a physical shop and I'm moving it to a web shop, to e-commerce, what are the additional risks that the assets that I care about, in this case, largely connected to my money, of course, what are the additional risks that I should now take into account? That is what we want to understand in computer security. How does the use of a computer system influence risk? And we do that by understanding two things. First, we want to understand what increases risks, and second, we want to understand how we can reduce risk. So the things that increase risk are called attacks or threats, depending on whether they're potential or actual. So an attack or a threat is a scenario that an adversary could perform to abuse, steal, or damage one of the assets. And if many of these scenarios are possible, either are happening in a system we are analyzing, or we can think of them in a system we are building, that's the threat side. So threat is potential, attack is actual. If many of them are there, clearly risk is high. If you cannot think of one possible scenario in which an adversary that you have identified could actually abuse, steal, or damage your assets using this computer system, then risk is low, right? So we try to get an understanding of attacks and threats in order to understand risk to assets. Right? And the more attacks and the more dangerous attacks you can identify, the higher risk will be. On the flip side, how do you reduce risk? You do that by imposing controls on the system. So you can think of controls as specs to what the system should do and not do in order to reduce risk. So anything you do as a defender when building or analyzing the system to reduce risk, we'll call that the control. And the best way to understand them is maybe to look at examples again, in, for instance, in a messaging system. So for attacks, I think you can come up with plenty of scenarios yourself. Somebody might be eavesdropping on messages while they fly over the network, for example. An adversary might be sending messages with a forged identity, maybe claiming to be from your bank to do phishing, for example. Adversaries might be using the messaging platform to send many, many messages, the well-known threat of spamming. They might use the messaging platform to spread malware and infect the client device as another asset that we cared about, and so forth and so forth. I'm sure you can think of more of these attacks yourself. And then controls are what you would, as a owner or defender, impose to reduce the risk of these attacks. And these are then things like protecting message confidentiality, making sure that any user that wants to use the platform is authenticated, so you verify their identity, doing things like spam detection. It's also not necessarily technical. I think Bart Peneel made in his lecture yesterday very clear that security is a very interdisciplinary discipline, so that is true here too, for example. So one control that is entirely non-technical is increasing user awareness. So it's well known that phishing goes down if people are aware of this threat. So this is a control that you may want to impose. You want to make sure your user base knows about this, so that the risk of successful phishing actually goes down. Okay, again, open-ended list, not intended to be complete. Okay, so you should think of attacks and controls as kind of specs, right? An attack is a specification of what an attacker could do to do something bad to your assets. A control is a spec of what the system should allow or disallow to reduce risk. The implementation part of this is what are called vulnerabilities and mechanisms, right? So a vulnerability is an aspect of the system itself, right? The system you are analyzing or building, and it's what you identify as the root cause of why a particular attack is possible. So vulnerabilities are the things in your system that enable a specific attack or threat scenario. Right? That's the general notion of vulnerability. And on the flip side, for the defender, we call that a mechanism. A mechanism is what you do in the actual system, something you implement in the system, for example, to comply with the control that you think of as a spec. So the control is the spec and the mechanism is the implementation. Again, examples may help clarify this. So for instance, weak passwords, the fact that users have chosen weak passwords in your system could be a vulnerability. If your system runs on unprotected network connections without additional measures like cryptography, then that's clearly a vulnerability. It's an aspect of the system. It sends messages sometimes over maybe unprotected Wi-Fi. Well, that would be a vulnerability of the system. Again, vulnerabilities can be non-technical if the system you're analyzing includes the user base, and the fact that maybe you have a non-technical user base might increase risk because they might not be aware of some of the ways in which these systems could be abused, right? And then the corresponding control would be to increase user awareness using a mechanism like user training, for example. So mechanisms are the implementation of the controls we just mentioned, like you might use cryptographic techniques to protect messages, you might use second factor authentication to counter the use of weak passwords, for example, you might do user training to increase user awareness, and so forth and so forth. Okay, so these are the key concepts I think are very useful to grasp when you work in security. Essentially what you do as a security engineer is, for the system that you're looking at, you're trying to understand each of these concepts. You might be doing adversary modeling, you might be doing threat modeling, you might be doing vulnerability analysis, risk analysis, asset elicitation, and so forth. So for the given system, you're trying to understand these things. Another thing worth noting here is, may have this on the next slide, is that it's very common in security that these controls and attacks evolve over time, including the corresponding implementations, right? Why? That is because we have this strategic adversary. No system will ever be fully secure. If you have implemented good controls, then what adversaries will do is try to creatively and strategically come up with new attack techniques, right? And so new attacks will arise, and you will have to come up again with controls that handle these. And this is called the attacker-defender race, and you see it in any sufficiently complicated system that has protection requirements. So this is an inherent aspect of security. And so you will commonly see controls and attacks that are like the flip side of one another. A control has been introduced specifically to counter an attack technique, or an attack technique has been introduced specifically to evade an existing control. Okay? So one possible definition now of software security is to say, well, so software security is just doing this for software-based systems. And then the focus might be on understanding the software in this computer system, the controls that apply to it, how you implement them, the attacks that apply to the system, and the vulnerabilities that enable them specifically for software. Right? And that's the first definition of software security we'll explore. So it makes sense to think of software security as really security engineering for software-based systems. And what I'll do is give an overview, again at a high level, non-technical, of a couple of the key controls that matter there. But it will turn out that one of these controls is maybe more important, or I shouldn't say that, maybe more unique to software than the others. And that's what we'll zoom in then on the third part. Okay, so we want to think about the security of a software-based system and think about potential controls we might want to impose on these systems. Of course, then we need to know what system we're talking about. And I want to be as general as possible. So what I'm going to do is I'm going to take a very generic model of the system. The system we want to protect is a piece of software that receives requests and sends out responses. And that's all I'm going to assume about the system. So that's a very abstract, but also very general model. And I hope you see it applies to many actual systems. For example, a web shop or any web application, you can think of this as a software system that receives HTTP requests that might encode requests like adding something to a shopping cart, checking out and paying, and so forth. Similarly, if the protected system is an intranet, then the interactions, the request responses will be network packets or setting up of network connections from internet hosts to hosts in the internet. An operating system kernel accepts system calls and sends responses back for these. A database accepts queries and sends responses back to these, and so forth and so forth and so forth. You don't need to understand all these examples, but it's good to have some concrete example in mind as we go over each of the controls on the next slide. Okay? Okay, so I'll discuss 4 controls briefly. Well, each time what I'll do is explain the control, try to motivate why it's important, discuss some of the mechanisms used to implement it, some of the attacks that might break it, and some of the vulnerabilities that enable these attacks. Right? And in that way, I hope I can give you a sense of the kind of things you do in this definition of software security, and also relate it to the concepts that we started with today. So what is isolation about? Well, software always runs on something, right? It runs on a host. And one of the things, so the key thing we want to achieve with isolation, so the spec essentially of isolation is, we want to be able to think of this protected system soundly as something that just sends, accepts requests and sends responses. In other words, you cannot interact with the protected systems in any other way than by sending a request or receiving a response through intended communication interfaces. That's what isolation is about. If there are other ways to interact with the system, we might not be thinking about them, and it's dangerous. So that's what isolation is about. And this is relevant in many scenarios. For example, software often runs on a platform where also other things run. This is true on an operating system. Your web server might be running as a process on your operating system. Many other processes might be running there. And even though you think of your web server as something that receives HTTP requests and sends HTTP responses, these other processes might have all kinds of other ways to interact with the web server. And isolation is making sure that cannot happen or does not influence security. Right? Similarly, if your system is actually physical and the only software running on it is your software, like maybe, for instance, in a smart card, then still it matters. Then you could say the host is physical, right? So there are no other stakeholders running on the same hardware as you. But still, if the system might be in the hands of the attacker, like a smart card, then maybe the intention of software on a smart card is that you interact with it through APDUs, application protocol data units. You send a smart card request, it sends you back a response. But if you have your hands on the smart card, you might do all kinds. You might measure power on it. You might try to take out the chip, shoot lasers at it, freeze it, and do whatever you want. Maybe to try to influence the state of the smart card, or to try to learn something about secrets in the smart card. So these are two examples where the isolation control is important. So depending on the host running your protected system, so what is running your software, you will use many different mechanisms for isolation. So on an operating system, this would be virtual memory and process isolation. On the cloud, it would be a hypervisor running virtual machines. On a smart card, it's physical isolation, so you would try to put physical boundaries around the chip so that it's hard to break into it. And there are other ways I mean, again, the list of potential mechanisms is open-ended. Attacks typically here are then what are called side channel or fault injection attacks. What the attacker tries to do is learn something about the system through a non-intended interface, that's a side channel attack, or influence the system through a non-intended interface, that's a fault injection attack. And that's, for example, shooting a laser at the chip, or measuring the time something takes to learn something about what is happening in the system. Right? And the underlying vulnerabilities, I'm not going to go deep into them. Depending on the host running your software system, different ways of learning something about what your software is doing might enable these side channels, and that are then the underlying vulnerabilities to isolation. Okay, so that's one example of an important control. A second example that I'll be brief about, because I think there are other lectures in this course is authentication. So with isolation, what we get is it is okay to think about our protected system as receiving requests and sending responses. Nothing else is possible. That's isolation. Authentication then is we want to know who is sending these requests and who can read the responses. Right? So authentication is about who, right? And that sounds simpler than it is, unfortunately, because this who question can have very, very different kinds of answers. For example, you might want to know who in the sense of what Belgian citizen with what ID card number, for example. Or you might want to know the user ID on your system. Or maybe you just want to know some attribute of the user, like he's a member of the CS department. Or maybe you're interested not in authenticating requests from people, but from machines. And you want to know what machine you're talking to, or what software running on that machine you're talking to, and so forth. So in general, the problem of authentication is tricky, because determining what kind of answer you want to this who question is already tricky. We use the term principle typically in the field of authentication as the answer to this who question. What are the potential principles in this system that we want to authenticate? And that can be people, or that can be machines, or that can be software or machine, and so forth. And then depending on the type of principle and the channel that you use to communicate, many, many different mechanisms exist, and I'm sure they will be covered in more detail in other lectures. But as a very simple example, if you want to authenticate a human over a local trusted channel, like when your smartphone is trying to authenticate you, or like when an ATM is trying to authenticate you, then things like a PIN or a password or biometrics are reasonable mechanisms. If you need to do that remotely, on the other hand, that's not a good idea, because maybe somebody can see the PIN while it's being transmitted. So then you need additional protections. If you want to authenticate machines, you will need different mechanisms. If you want to authenticate code, you will need different mechanisms, and so forth. Right? Attacks, again, probably covered in more detail in other lectures, things like password guessing, replay attacks against cryptographic protocols, and so forth and so forth. And the underlying vulnerabilities are, for example, bugs in protocol implementations, the use of weak passwords I mentioned before, and so forth. Okay, so that's control of authentication. So what do we have now? We know we can think of the system as processing requests and sending responses, and that's all. We know who is sending these requests and who is reading the responses. So the next control is we want to enforce that only that somebody can only do something, send a request or have a request executed by the system if that is allowed. That's the authorization part. And authorization, of course, is application specific. What somebody can do on a system depends on the application. So this is parametric in what we call a policy. Something should specify which behaviors of the protected system, who can ask it to do what, and so forth. And then depending on the type of policy, you'll have, again, plenty of mechanisms. So the most typical type of policy is what is called an access control policy. And that's a policy that will say who can do what kind of request, right? So we have the answer to the who question already. Now the policy tells us, given a principal and a request, whether that's allowed, yes or no. For instance, if the system is a social media platform and somebody asks to see the timeline of a user, then the rule might be only friends of that user can see the timeline. So you have all the information to make that decision, and you would typically implement that using something that's called a runtime monitor. So there can be a piece of software that collects all this information and makes a decision. Right? But that's not possible for all kinds of policies. You have more complicated policies, for instance, liveness availability related policies. So you might have a policy that says certain requests should be handled promptly, like it's important to handle a payment request promptly. This is not something you can handle with a runtime monitor. A runtime monitor cannot speed something up. That's just undoable. So there you need other mechanisms. And one that you might use is analyze the code that will process the request to make sure that there are no unbounded loops, no blocking waits, and these kinds of things. And that may give you some assurance that you will handle them promptly. Okay? And there are many other kinds of policies that you can think about. Attacks against authorization, again, there are many of them. A famous one is what is called the confused deputy attack. This is essentially the idea where you are not allowed to do something, but some other principal in the system is allowed to do it, and you trick the other principal to do something in your place, essentially. That's the general idea of a confused deputy attack. Or forceful browsing, some of you may have seen, is if you're not allowed to access a certain document, say on a newspaper, sometimes by going directly to the URL of that document rather than going through the normal channel of going to the homepage of the newspaper, you might still get access anyway, right? So you bypass the authorization check in a sense. Is another example of an attack. And so the underlying vulnerability in that case, in the forceful browsing attack, is something that's common in authorization. It's called incomplete mediation. So if you do this runtime monitor approach to access control, one of the challenges is to make sure that you do these checks at all points where they're necessary. Right? So if you miss a spot, that's called incomplete mediation, and then clearly your authorization control might fail. Right? Another typical example of a vulnerability in this setting are configuration mistakes. So you might actually be enforcing a policy, but maybe you specified the policy incorrectly, and then clearly again there's a vulnerability in your system that might be abused by attackers. Okay. Finally, the fourth control I want to say something about, and I'll be brief here because that's what I'll dive into in more detail in the next section, is implementation correctness. So what is that about? Well, we already know, isolation, that we can think of the system as just receiving requests and sending responses. We know authentication, who is sending these requests and who is receiving the responses. And we know, and we have ensured, that only somebody who's allowed to do something can actually do it. That's the authorization part. The final missing piece of the puzzle is, so now you have decided that a specific request is okay and it can go through. Is the implementation of that request correct, yes or no? And this is much more tricky than you would expect at first sight. So first, it's obvious that you need something like that. It's a very stupid example. Suppose the request is a read, but the implementation of the request actually does a write, then clearly all bets in terms of security are off again. So you need to know that the implementation of a request does what the request is intended to do. Right? And it turns out that it is much harder than you think to do this if you are up against a strategic intelligent adversary. So we'll see examples of where adversaries choose request parameters and inputs to a request maliciously, such that the implementation of that request does very weird things. And a surprising thing is that generic classes of bugs, and these are called software vulnerabilities, actually enable very powerful changes to what the implementation of a request does. Even may enable you to completely take over the protected system in a sense. And there are plenty of types of these bugs, and these are then also the attacks and underlying vulnerabilities. So I'm sure some of you will have heard about buffer overflow, the corresponding vulnerabilities that you manage memory badly. The corresponding attack is called a buffer overflow attack. Well, I'm not going to discuss these in detail here, because this is an example of what is called a software implementation vulnerability, and some people would say this is actually really the core of software security. The fact that you have these simple bugs that can have such disastrous consequences is really what is unique for software, and is what should be the core of the software security field. Yes.
I understand the concept, but nevertheless, with the rise of AI and now with GPT 5.5 and whatever, I expect that yes, there are still lots of vulnerabilities which are dependent on the flow and on the business you want to have, but then the generic vulnerability, I would say those are going to be basic hygiene. It's as if we build this building and we say, okay, if I walk on the stairs, the whole building should not fall down. This is like the basic stuff
Yeah.
that we shouldn't do. And I think we have walls for, let's say, physical structure. We had those problems some centuries ago. We solved them, and now I expect that with AI, we move from those generic vulnerabilities to some more sophisticated.
Very good point. I would say, and actually I'll come back to that in a minute. Very good point. So the point is, well, maybe the generic vulnerabilities will all disappear thanks to AI. So we'll move to more application-specific logic flaws and things like that. I would say the jury is still out. So what we have today is AI can find these vulnerabilities. We all heard about Mythos and all the panic around that, and even the weaker models are relatively good at finding these vulnerabilities. At the moment, the reaction is not, oh, nice, now the basic hygiene problem is solved. At the moment, the reaction is panic. And how that will evolve is hard to predict. I mean, I know this field well, but I've been really surprised by what generative AI models have been able to do in terms of security, and whether they'll be more useful to the attackers or more useful to the defenders, I don't know.
Cyber is actually better than Mythos because it's going to tell exactly what exists, how to solve it, and also how to detect it.
Well, how do you, yeah.
It was not available, now it's available in 5.5.
And probably further evolution will happen in the coming months. So I talked to some people who were involved in the Glasswing project, where people could, and I think the conclusion, there is no conclusion yet. So I have in my conclusion that we are kind of on a break point in this field, right? What will happen? And I have a couple of slides. So you're early with your question, but it's a very valid point. But I wouldn't be assured at this point yet that the basic hygiene things will be solved automatically. We'll see. We'll see. Yeah. 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 Yeah.
So I have a related question, and that is that we were talking about software security, but the very nature of software is changing. Because right now we have software agents, right, agentic AI, and it's doing completely different things than what software used to be doing. It has agency, and that therefore you have to deal with identity, perhaps. Identity management will become a security issue. Agents work together, so that adds another layer of complexity to software that we didn't have before. How do you see that develop?
Yeah. So first, very good point, and I agree to some extent, not completely, because it's not the first time that software is working together, right? I mean, one of the reasons why the impact of software vulnerabilities in the past has been huge is because we've been building distributed systems for 30 years at least or longer, and software talks to other software, and that's one of the ways in which, for instance, malware can spread. So the fact that so there is fundamentally new things. I completely agree. The way in which so what I'm saying here is, for software as we've been writing it till last year, let's say, that kind of software will persist for a while because we have a huge amount of software that was written that way out there. What I'm saying is to some extent relevant to AI agents themselves. So how AI is something very different than classic software, and I think a whole new range of problems surface there. And there's a separate lecture on that later in this course on AI and security, which I think, is partly overlapping and partly orthogonal to what we have for classical software security. Yeah. So yeah, it's a exciting new world for security. So most of the things I'll say and the examples I give here of vulnerabilities are indeed for software as we have been writing it for the past 50 years and not for machine learning models that we prompt. They have their own breed of problems and later lectures will come back to that. Okay. Okay, so let's dive into this area of implementation vulnerabilities. Actually, some of the things I'll say we've had in this discussion, so I can go over that quickly. So what is a software vulnerability? We discussed this. It's a bug, a defect that leads to a potential attack technique that's maybe more powerful than you would expect. So surprisingly, some of these attack techniques are very generally applicable, and that's what makes the study of this field very important. So a more narrow definition of software security might be to understand these software vulnerabilities and how they can be exploited. And it's not unlikely that, for example, AI models will also have generic classes of vulnerabilities that allow you to jailbreak them or do other things to them, but I won't be discussing that class of software in this talk. So first, why are vulnerabilities? So I want to convince you that first, there are plenty of vulnerabilities, and two, they are dangerous, right? Maybe that's preaching to the choir, I'm not sure, but it's an introductory lecture, so I want to make sure I convince you of that. So first, that there are plenty. Evidence for that is, for example, the CVE list. I think Bart talked about this yesterday and even had a graph of the growing number of vulnerabilities in CVE. So CVE is the common vulnerabilities and exposures. It's a list of vulnerabilities in widely used software and hardware. So it's both software and hardware, but the bulk is software. And at the point where I made this slide, so earlier this month, there were more than 300,000 of them in the CVE database. So there are plenty of them. They're dangerous, at least a significant fraction of them. And I want to show that with two historical examples. So and I hope that these also give you an idea why a simple bug can be so disastrous. So a very famous example is Heartbleed. Heartbleed was what is called a buffer overread attack. It's related to the fact that some languages do not check how your software accesses memory. If I have time, I'll come back to that in a bit more detail later, but for the moment, I just want to show you the gist of the attack. So because it's actually quite simple. The underlying vulnerability was an implementation bug in the implementation of the TLS protocol, more specifically in the heartbeat subprotocol of TLS. And what that protocol does is very simple. A client can send a request message. Part of that request is a payload, in this case 9 bytes. The server just sends a response. Part of that response is the payload, and the purpose of this protocol was to check that the connection is still alive. So it's like a ping pong, a heartbeat, hence the heartbeat subprotocol. Now, what was the bug in the implementation? The bug was very simple. A client, when it sends such a payload, also specifies the length of that payload. But of course, a client can lie about that. That's what's happening in this message. This is only 9 bytes long, but the client claims it's 65,000 bytes long. Well, the bug was that the server, the receiver of the request, did not check whether this length was well correctly specified. And a consequence of that was, what the server does is, he reads this payload into memory and then sends it back, but uses the incorrect length to send back the payload, and that means he's actually sending back the payload, and then 65,000 bytes that are in memory, that happen to be in memory right next to that payload. So essentially what the server is doing is dumping a part of its memory to the client. And then if in that memory are critical secrets, and in the case of Heartbleed that was the case, more specifically there was the possibility that the private key of the web server was in that memory, then essentially you send your private key to the client, to the attacker, and it's game over in terms of web security. So the point here is a very simple bug. Essentially, you forget one check, and it's game over for the security of your system. And there are many other examples of that. And another famous example is stage fright. No details about the bug except the potential impact. So this was a bug discovered in 2015. At that point, it was on 1 billion smartphones. And it had been present in the source code of Android since 2010, for 5 years. So for 5 years, 1 billion phones are vulnerable. And the effect of this bug was, if your phone had this bug, an adversary could send a message to you, a maliciously chosen message, which allowed the adversary to completely take over your phone. We'll say a bit more about how that is possible further on, but for now, you'll have to believe me on that. So we call that hacking or pawning or exploiting the vulnerability and and really taking over the phone. And the fact that this is possible because of a single bug is a very important contributor to risk in software-based systems. And that's why the study of vulnerabilities, their exploitation, and the countermeasures is by some seen as the core of the software security field as a whole. Okay, so this relates to the discussion we just had. So finding these vulnerabilities, if you have a vulnerability that the producer of the software is not aware of, if you have a vulnerability in Android that Google is not aware of, it's called a zero-day vulnerability. The producer of the software has been aware of the vulnerability for 0 days. Then that's like a weapon. It's like a burglary tool. You can break into systems. And of course, that's very valuable, right? Being able to break into everybody's phone is a very valuable authority, right? And so what we saw over the past years, and I think Bart mentioned this in his introductory lecture too, is that there's a whole market for these zero-day vulnerabilities. So software producers will pay you for them. So here you see numbers from the Google Bug Hunters problem. They paid out over $80 million in rewards for finding these kinds of vulnerabilities. But you can also send them to people who make tools to break into systems like Zerodium. So they will pay you for a zero-day vulnerability and then build a tool with it that law enforcement or others can use to break into systems. And this is a point where we are really at a turning point because of AI. What we now see is that generative AI tools can find vulnerabilities so quickly that this will disrupt the vulnerability market, and it's unclear to me what will happen there. So for instance, the prices from Zerodium here are old ones. Since a couple of months, Zerodium has taken its price list offline. Probably, again, I have no insight on this, but probably because of the evolution that we see in AI-based systems. So what will happen now that generative AI tools can find these vulnerabilities much faster? Will they become worthless? Will they become more valuable? I don't know how to predict this. This is a disruption in the zero-day market has been ongoing for decades, actually. But what is happening today will disrupt this in ways that I don't feel comfortable making predictions about. Yes.
Last year, CISO published over 1,500 non-exploitable vulnerabilities, which was triple than the previous year and the statistics. Now, when we look at Mythos or any other application, basically they are still discovering exactly what we know as non-exploitable vulnerabilities. This is just to say that yes, the tools for identification will improve, but on the other hand, in industry, the real challenge will stay how to mitigate them because of the simple complexity and dependencies. And at some point, as we also showed in the very beginning, there is always a question of how worth the asset is and how dangerous is the changes in the asset. And most of the time, the decision is, well, solving this is actually a higher threat because it might break the actual business.
I completely agree. And that's why I say I don't know how to deal with this. So I think the first reaction we see is people are thinking, okay, we should solve this wave of vulnerabilities coming our way. But I agree with you, it's unclear that is the best course of action. But I wish I could tell you what to do and predict what the future will bring in a couple of years, but I can't. I think this is really a new turn of events. Okay, so let me use quick. So I only have 30 minutes left. I wanted to give a couple of examples of actual implementation vulnerabilities for those of you who have not seen examples. Let me make sure that I can at least get through one example that's very easy to understand, and we'll see how much time we have left. So I wanted to discuss the two most important classes of implementation vulnerabilities today, which are structured output generation vulnerabilities and memory management vulnerabilities. These are the ones that have been exploited over the past decades, definitely most. Structured output generation vulnerabilities are the simplest ones. What are they? Well, very often programs, software, generate outputs that will be consumed by other programs. For example, your program might generate as output a SQL query that will be consumed by a database. Or your program might generate HTML that will be consumed by a browser. Or your program might generate a bash command, a shell command that will be consumed by the operating system shell. right? So this is a common programming pattern. And if you do that kind of, the construction of that kind of output using string manipulation, this is known to be very hard to do correctly. If attackers can choose some of the input strings to that string manipulation, it's very likely that they will be able to change the structure of the output in a way that changes the intention of what the program wants to do. And I'll give a concrete example of that, and then I'll generalize. So here is a very concrete example, the simplest one to understand, the SQL injection attack. What you see here is the architecture of a typical web application. So we have some code running in the browser. We have an application server running JavaScript or Node.js, for example, and then we have a database used to persist state of the application. Now, it's common for the code in the application server to generate queries for the database. And here is a very simple one-line statement generating such a query. This might be part of the authentication part of the application. So what this does is it gets a name and a password from the browser, and it creates a query that looks in the users table whether there is a record with that name and password. So the idea is, if we send this to the database and a record comes back, we have a valid name-password pair. If no record comes back, we can say, oh, we don't know you, please make an account, or wrong password or whatever. Right? That's the idea of this code. Very simple code. So how it would work normally is, the browser shows a form, you type a name and a password. This gets plugged into by the application server into the SQL template here, and it gets sent to the database in this form. And this is how it works correctly. Now, many of you will have seen that this one-line program is of course buggy, but it's not that easy to see if you've never seen an injection vulnerability before. So why is it buggy? Well, if the adversary is strategic and intelligent and can choose these inputs maliciously, all kinds of shit can happen, right? So here is an example. If the adversary chooses the name string to look like this, and you'll see in a minute why it looks like this, then of course this code will run like before, and it will generate a SQL query like before. Essentially, this will be plugged in here, and this will be plugged in here. But what we see now is that this quote here now actually closes this quote. And the two dashes here are actually a SQL comment character. So essentially this part of the query gets ignored, and what you send to the database is really this. So this is really simple, and of course many of you will have seen SQL injection before, but if you haven't seen this, this is a good illustration of how a very simple bug, easy to overlook, can completely dismantle your security. Because now what this will do is it will give you back a record if it exists for this name, and you don't need to know the password anymore. So the net consequence of this injection vulnerability is that an attacker can log in as any user as soon as he knows the username, and he doesn't need to know the password anymore. Right? Yes? No. So well, unless other defenses are in place, what you have here is code that's executing this. All the attacker does is on their browser, so this might be Amazon, this might be a web application. Of course, Amazon has defenses against this. A web application. Yes, exactly. So this is the base vulnerability, and there are plenty of controls you can implement to make sure that so, and this is an example of, so this was more dangerous at the point where this attack technique was discovered, because no specific controls to defend against this were in place. And that's the attacker-defender race I mentioned before. Every old vulnerability, if you give a simple example of it, there will be in modern systems controls that stop it. On the other hand, very often, there will be variations of this attack technique that bypass these controls, right? And then there will be new controls that stop these new attack techniques. For example, for SQL injection, a typical variation that came later are what are called higher order injections, which I don't have time to go into, but in any of the fields, so memory management vulnerabilities, structured output generation vulnerabilities, you will see this evolution. You have the discovery of the vulnerability. The essence of it is simple. People come up with controls. They solve it to some extent. Attackers think, oh, but we can also do this. You have more complicated variants of the attack that bypass it. And this is in a sense unavoidable, and it's what I called before the attacker-defender race. And you're right that this very simple form of SQL injection will not work in modern systems. Well, if that works on your system, you're in very bad shape. Well, yeah, I also know people who are still chasing these kinds of bugs in their system. But the state of the art indeed, well, that means that you're not at the state of practice in terms of security. Yeah. Yeah.
Cover these kind of things. So, like, how do you think, like, the software developers or like our development practices can improve? Because these are like attacks from like 20 years back.
That's the million-dollar question, right? So what you say is we've known this, and it's even worse for memory management vulnerabilities. We've known about them for 40 years or so, and Microsoft publishes their security reports every year. I think over the last 5 years, 70% of the successful exploits and critical vulnerabilities are still memory management vulnerabilities. So I agree with your observation. In a sense, these issues are simple. I called them generic before. We observe that they don't get solved. It's not that we don't know how to solve them, but there are plenty of... So for example, for injection vulnerabilities, one powerful mitigation is there are APIs to construct structured output. If you use these rather than string manipulation, you have very little chance of having this kind of problem in your code. Similarly, for memory management vulnerabilities, we have languages like Rust or like Go or like that. If you program in these rather than in C, it's very unlikely, not completely impossible, it's very unlikely that you have that kind of problem in your code. So we have like list. So actually, I'll have a reference to the Cyborg software security knowledge area that lists all the defenses that we know. We know how to prevent them. We know how to detect them. We know how to mitigate their exploitation. There's a whole bunch of techniques. But practice shows that it's really hard because there's a bunch of legacy code, because there's a bunch of developers that are not aware of the issues. It's really hard to get to a stage where the basic hygiene is good enough that we got to get rid of these. And so, as we heard, maybe AI will solve it for us. I remain skeptical for now, but it might. Maybe if AI checks every code, every line of code out there and every new line of code written, maybe some of the basic things will go away. But yeah, I have no clear-cut answer for you. If I had an answer to that question, I'd be rich. Yeah. Bounty programs have shown to be effective in the past and are likely to remain effective. On the other hand, a challenge with bounty programs now is, well, people can now use an AI model to generate many bugs that they can submit to a bounty program, and the people will have to triage them. And who will AI triage them, or will people do it? If people do it, they're up. I mean, it's a tricky problem. It's really a tricky problem. Yeah. Okay, unfortunately, I also wanted to say, kind of do a similar tour of memory management vulnerabilities, but I see I have 3 minutes left, so I'm not going to try to do that. I had some examples of vulnerable code and how to exploit that. In a sense, a bit more technically detailed than a SQL injection vulnerability, but also kind of to explain you the essence of what can go wrong here. And the bottom line is the same. Very simple mistakes can lead to disastrous consequences, right? Maybe this is still important to mention. So as I said, if you want to know more about what is known to defend against these things, there's a bunch. We can prevent, we can detect, we can mitigate. I'm not going to try to cover that in this talk. This is an introductory talk, but there's in the cybersecurity body of knowledge, so this is a project from the UK, there is a software security knowledge area that's available online for free that kind of gives an overview. And there's an old version that's available today, and there's a new version that will be published in the summer. And it kind of gives references to other documents, of course, because this is a wide knowledge area. But if you want to know more about what is known about defenses, then this is a good point to start. Okay, and then let me wrap up. So I hope with the introduction I convinced you that cybersecurity itself is a broad, interdisciplinary and interesting field where you have threats and controls that can be technical but also non-technical. I defined software security as the subfield of cybersecurity, and I explained to you that you can interpret it in two ways, broadly or more narrowly, as the general security engineering for software-based systems, or just the study of implementation vulnerabilities. And a very important conclusion point, but we already discussed it extensively, is we are at a turning point in this area. With the increasing power of generative AI, this field will change, and I don't know how it will change. And well, in 2 years, when this course happens again, I can tell you what will have happened. Okay, with that, I want to stop. There's still a bit of time for questions if there are any remaining, or you can also grab me right after the talk if you have a question you prefer to ask offline. Any remaining questions right now? If not, off to lunch.